Diagonalization of symmetric matrices. What is a symmetric matrix? It's not a new term for us. A matrix is symmetric when A equals A transpose. That's the definition of a symmetric matrix. Let me just write this up a little bit higher. Okay. So now we can come to this theorem right away. Nice theorem. We'll prove it with a 2 by 2 matrix. This theorem says that all roots of a characteristic polynomial have real roots. Remember, there's no reason why the characteristic polynomial can't be lambda in theory for a non-symmetric matrix. It can't be lambda squared plus 4. And I can give you a determinant that will give you that. Here's lambda squared, and I'll have 2 and negative 2. So you get this squared, lambda squared, minus negative 4, which is plus 4. And it's supposed to equal to 0. And if we're doing lambda, if we got this determinant from lambda I minus A, I can tell you what A is. A is going to be 0, negative 2, positive 2, and 0. Because when I take this away from lambda, I'll get this matrix. Okay, so there's a matrix. It's not symmetric, but there's a matrix whose characteristic polynomial is this. And remember that to solve this, lambda squared will be negative 4. And there's no real number that you can square to give you negative 4. So there's no real solutions. In this case, this matrix A, the characteristic polynomial of that matrix A does not have real roots. Some can. It can be a non-symmetric matrix and you get real roots. Like I could have made it be lambda squared minus 4, the determinant, or the characteristic polynomial. Okay, so we want to prove for a 2 by 2 matrix that this is true. And we just write down a matrix A that happens to be symmetric, and we take it from there. Proof for 2 by 2 matrix. If A is symmetric, then A would equal to AB, BA. Sorry, it doesn't have to be A, BB. If you look at the first row, it's AB. So the transpose would have AB as the first column. If you look at the second row, which is BD, the transpose will have the second column as BD. Well, you know what? That's A. It's A, and it's A transpose. So that's the only type of matrix. This is the only type of matrix that would work. I mean, basically, you put down something arbitrary for the first row. Or if you want to start with the second row, you can do that. You put down something arbitrary for the first row, like XY. And whatever you put for the first row, it has to be the same as the first column. And whatever you put for the second row has to be the same as the second column. And no matter what you put in this last position, the second row and the second column are both the same. So that is the only way to get a 2x2 symmetric matrix. Well, let's find the characteristic polynomial. Let us calculate lambda I minus a, the determinant of that. Well, first let's figure out what lambda I minus a is. So basically, you write down negative a, which is negative a, negative b, negative b, negative d, and on the diagonals, you add lambda. So this determinant will equal to this determinant, which equals the number 0. Well, that determinant comes from multiplying those two, and you get lambda minus a times lambda minus d minus the product of those two. The product of those two is b squared. Okay? So to save a little space, I'll go across. If you FOIL this out, you distribute that out, you get a squared minus a plus d lambdas plus ad. Don't forget minus ab. Minus b squared. Minus b squared. So this is the constant. So in terms of their quadratic formula, a is 1, b is negative a plus d, and c is a squared minus ab minus b squared. So what we want is lambda is equal to negative b plus or minus the square root of b squared minus 4ac all divided by twice a. Negative b. Well, b is negative a plus b. With a negative in front, it becomes plus a plus b. Plus or minus the square root of b squared. And when you square negative a plus b, you get the same as what you get when you square a plus b. Because when you square 5 or negative 5, you get the same answer. Okay, minus 4 times a is 1, times c, which is, here I'll factor out the b. I get b times a minus b. And all of this gets divided by twice a. A is 1. Okay, let's go to the top. And what we want to show is that this has two real roots. Well, how do you get how do you get a non-real root? That is, how do you get an imaginary root if what's underneath the square root sign is negative? So that's what we have to look at. And we can continue with what we're doing, but we need to really look at just what's underneath the square root sign. When you square a plus b, you get a squared plus 2 times ad plus d squared. And this messes 4b. Let's call it negative 4b. Times a is negative 4ba or negative 4ab. Plus 4b squared. Plus 4b squared. Okay. Apparently, according to my notes, I have a typo. We have to figure out why. This entry that I'm erasing is supposed to be a D. At least that's what it says in my notes. So, let's just look at this again. I'm sorry. The determinant was lambda minus A times lambda minus B minus B squared. And this was 0. If you compute the determinant, if you multiply this out, I meant to say, you get lambda squared minus A plus D. Lambda plus AD minus B squared. Okay, so yes, sorry, it is AD. It is AD. So, the biggest mistake, or the only mistake I had, was down here, because I'll show you in a moment, it was not the case that I can factor out a B. When the D was a B, when you had AB minus B squared, you were able to factor it out. So that was my typo, and let's fix it up. It's AD minus B squared. Everything on the bottom is now correct. Let us clean it up a little bit. So part of what I have on the top is wrong. So far what's underneath that square root sign is A plus D squared. And we are supposed to take away 4AD. Take away 4AD. And we're supposed to add 4B squared. And this all gets divided by 2. 2 times 1, 2. Okay, so what we get is A plus B in front of the radical. Under the radical, we have A squared plus 2AD minus, this was supposed to be 4AD. I don't know what's going on with me. Look on the bottom. It's minus 4AD. And if you have 2 ADs and you take away 4 ADs, you're at negative 2 AD plus B squared plus 4B squared. And here's where it's all going to come together. We have A plus B plus or minus the square root. Now, this part here is a perfect square. It's A minus D squared, which is never negative. And 4B squared is never negative. And when you add two numbers or two values that are never negative, you won't get a negative answer. That is the value of lambda. Those are the values of lambda for each and every symmetric 2x2 matrix. You just have to type in the A, B, and the D. You just have to type in the A, B, and D. Okay, so we figured out what lambda is. And the next line I'm going to say that what's underneath the square root sign is non-negative. Okay, A minus D squared is greater than or equal to 0. 4B squared is greater than or equal to 0. You keep adding these things that are greater than or equal to 0, you get greater than or equal to 0. A minus D squared is greater than or equal to 0. 4 times B squared is at least 0. B squared is 0 or more. Multiply numbers 0 or more by 4, and you will get 0 or more. 4 times 0 is not 4. So when you add these, when you add the left-hand sides, it's going to be bigger than what you get when you add the right-hand sides. When you add two zeros, you get 0. So what's underneath the radical is never negative. That implies that lambda has two real valued roots. And this is true for any square matrix, no matter what the size is. If it's a, now of course we're talking about any size symmetric matrix. If you have any size symmetric matrix, 4 by 4, 9 by 9, 17 by 17, the characteristic polynomial will have real roots. Now, why is it always a square matrix? Well, if A is m by n, and A transpose is R by S, well, I can proceed that way, but let's just switch these, n by m. But A equals A transpose if it's symmetric. Well, that implies that the size of A must equal to the size of A transpose. M and N must be equal to one another. And he says it again. M and N must be equal to one another, which means A is a square matrix. The only way matrix A can equal matrix A transpose is when A is a square matrix. I'm not saying all square matrices are symmetrical. I'm saying a necessary condition for A to equal A transpose, that is, for A to be symmetric, a necessary condition is that A is square. It is not sufficient. It's not enough for A just to be square. Okay. Now there's a consequence to that theorem. Remember, consequences of a theorem is called a corollary. If A is a symmetric matrix, with distinct eigenvalues, that is, they're linearly independent, and there's n of them. If A is an n by n matrix with distinct eigenvalues and symmetric, then A is diagonalizable. We're not going to prove this, but all you have to do is realize that if A is symmetric and it has distinct eigenvalues. Now, what will it mean for it not to have distinct eigenvalues? If you have lambda squared times lambda minus 3 squared equals 0. If this is the determinant of lambda I minus A, the determinant of lambda I minus A equals what I wrote, which we said equal to 0, then the eigenvalues will not be distinct because you have lambda. So this is a 4th degree polynomial. So in a way, you get 4 different lambdas. Lambda can equal to 0, and lambda can equal to 3. But the multiplicity of when lambda is 0 is 2. That is, lambda equals 0 comes up 2 times. lambda equals 3 came up 2 times. So if you found an eigenvalue, an eigenvector, associated with lambda equal to 0, and you found an eigenvector, call it x of 3, for lambda equals to 3. When you go to find a matrix P for diagonalization, you just can't put x1 and x3 because it's a fourth degree polynomial. You have to put 4 of them. Okay, you have to put the eigenvector that was associated with lambda sub 2, which is also x1. You also have to put x sub 3 again. Okay, this would be what P is. Now, the original matrix A is diagonalizable if and only if these eigenvectors are linearly independent, and they're not. Now, I did say something that if somebody's really up on things, they'll say I made a mistake. I said because it's a fourth degree polynomial, you have to get 4 eigenvalues. Well, that's true, but we're not talking about when you get complex eigenvalues. But we really found 4 distinct roots, real roots. We found, well, let me not say distinct. We found 4 real roots. And after all, this is lambda times lambda minus 3 times lambda minus 3. There are 4 factors, and each one of these factors give us a real root. 0, 0, 3, and 3. Okay, so if A is a symmetric matrix, and it has distinct eigenvalues, and A is diagonalizable. Okay, we're not going to prove that. The little piece of the proof, I didn't even talk about it. But you don't have to know how to prove that. Hopefully it's in your textbook if you really want to know it. And now, another amazing theorem. All these connections come together. All these concepts come together. Theorem. If A is a symmetric matrix, then the eigenvectors that belong or associated with, that belong to distinct eigenvalues of A are orthogonal. That means if you have lambda squared, if the determinant of lambda I minus A is equal to lambda squared times lambda minus 3 to the 4th power times lambda plus 1. The distinct lambdas are 0, 3, which came up 4 times, and negative 1. You find the eigenvalues associated with those 3 eigenvalues. Maybe I said that wrong. Find the eigenvectors associated with these 3 distinct eigenvalues. Those eigenvectors will be orthogonal to one another. Those eigenvectors will be orthogonal. So if you have a symmetric matrix and you calculate the eigenvalues without using duplications, if you find their eigenvalues, the eigenvectors for all those distinct eigenvalues, those vectors will be orthogonal. Let's look at this example. Suppose A is equal to this matrix. So let's find the characteristic polynomial. So we look at the determinant of lambda I minus A. Oops. Well, here is negative A. And, oops, negative 1. I had lambda on my mind. And on all the diagonal entries, you put lambda. The best way to calculating this determinant is to use, forget what they call that technique, but we'll expand cofactor expansion. We'll expand about the last row. Now let me make it clear that it's not 0 lambda, but rather the last entry is lambda minus 1. We expand about the last row. Now there's no reason to expand about the first, to cross off the first column, because we have a 0 here. Same argument for the second column. But then we have to do the third column. So what we get is negative 1 raised to the position value. That value, lambda minus 1, is in the third row, third column. And it is lambda minus 1 times the determinant of what remains after you cross off the third row with the third column. Namely this. Lambda minus 1, minus 1, minus 1, lambda minus 1. Okay, negative 1 to the 6 is positive 1 times lambda minus 1 times the determinant. The product of those two entries, lambda minus 1 times itself, minus the product of these two, which is 1. Okay, so what we get is lambda minus 1 times lambda minus 1 squared, is lambda squared minus 2 lambda plus 1, and then take away 1. Just take away the 1. So we have lambda minus 1 from the front, and in here, that's the whole thing, I can factor out a lambda, which I'll put in front, and then I'll be left with lambda minus 2, because lambda minus lambda is lambda squared minus 2 lambda. And this is supposed to equal 0. So either lambda is 0, which occurs when lambda is 0, or lambda minus 1 is 0, which happens when lambda is 1, or lambda minus 2 is 0, which happens when lambda is 2. Okay. So I have the 3 eigenvalues, and if any of them were repeated, I would cross it out. My goal is just to show that the eigenvectors are going to be orthogonal. Okay. So now, let's talk about when lambda is 0. If lambda is equal to 0, we want to solve A minus lambda I augmented with the 0 vector. But 0I is the 0 matrix. A minus the 0 matrix is just A. That is, we want to solve this. 1, 1, 0. 1, 1, 0, 0, 0, 1, augmented with the 0 matrix. Well, right away I see two rows are the same, so if I subtract those rows, I'll get 0. If I do row 2 minus row 1, I'm going to get a row of zeros. So the first row isn't going to change. The third row, I'll actually put second. And the last row is going to be those rows or zeros. Okay, that's done. Okay, well if I call the variables x, y, and z, column 2 does not have a leading 1. Row 1 has a leading 1. Row 2 has a leading 1. Column 1 has a leading 1 for row 1. Column 3 has a leading 1 for row 2. Column 2 does not. That is, y is equal to r. And the first row says that x plus y is 0. That means x is negative y. X is negative y. But y is r. And the second row says z equals 0. Z is equal to 0. Okay, z is 0. So what I get is r times negative 1, 1, 0. So I'll call that the eigenvector. X associated with lambda equals 0 is negative 1, 1, 0. Now, let lambda equal 1. If lambda is equal to the number 1, we have a minus 1 times I, which is just I, augmented with 0. So I just take away 1s from the diagonal. I take away 1 from those entries, and they're all going to become 0. So I have 0, 1, 0, 1, 0, 0, 0, 0, 0. I augment this with the 0 matrix. Now, if you want to say that that's not in RREF form, fine. But the bottom line is we have all the answers. This tells me that x is 0. This line tells me y equals 0. And I'm told nothing about z. In column, row 2 has a leading 1. Row 1 has a leading 1. So column 1 has a leading 1. It's in row 2. Column 2 has a leading 1. It's in row 1. Column 3 does not. That is, z can be r. So we get that x associated with lambda equals 1 is 0, 0, 1 times r. So that's the next eigenvalue. Well, let me just put the big equal sign here, and then say that x1 is 0, 0, 1. Now we have to find the eigenvalue, the eigenvector when lambda is 2. What's the eigenvector when lambda is 2? Lambda is 2, so we want to solve a minus 2 times I augmented with 0. That is, from a, I take away 2 from all the diagonals. And if you have 1 on the diagonals and you take away 2, you'll get negative 1. And by the way, this is A transpose. If you switch the rows and the columns, you'll get A transpose. So what I have is negative 1's on the diagonal and nothing else changes. 0, 0, negative 1. Okay. If I put row 2 first because it has a 1 instead of a negative 1, or if I just multiply row 1 by negative 1, I get that. And so I just multiplied this by negative 1. I'm going to put this in the second position, except I'll also multiply it by negative 1. And then if I add those two rows, I get a row of zeros. Okay, column 1, row 1 has a leading 1, and row 2 has a leading 1. Column 1 and 3 have a leading 1. Column 2 does not. I do have one little typo. This should be augmented with the zero matrix. And the answer is nice and easy. The second row tells me that z equals 0. Or the fact that the second column doesn't have a leading 1 tells me y equals r. And row 1 tells me x minus y is 0. That means x equals y. But y is r. So this gives me r times 1, 0, 0. And that right there will be x of 3. So I have x of 2. Lambda happened to be 2. So I have the eigenvector when lambda is 2. I have an eigenvector when lambda is 0. And I have an eigenvector when lambda is 1. Any two of these have a dot product of 0. Any two of them have a dot product that equals 0. After all, that's what an orthogonal set means. It says the eigenvectors, which is the set, will be orthogonal. Any two eigenvectors that we dot will give us 0. Now I call the eigenvectors x0, x1, and x2. So we can dot x0 with all other eigenvectors, namely x1 and x2. And we can dot x1 with all the other eigenvectors, namely x0. But remember, dot products commute. That is, x1 dotted with x0 is x0 dotted with x1. So I don't need to write x1 dotted with x0. Don't dot x with itself. Don't dot x1 with itself, because nobody ever said that had to be orthogonal. In fact, they'll be parallel. Dot it with x2. So x0 is negative 1, 1, 0. I dot it with x1, which is 0, 0, 1. Multiply those numbers, you get 0. Those two, you get 0. Those two, you get 0. Add them up, get 0. So on a roll. I take x1 and I dot it with x2. And then I get nervous because it's not working. Oh, okay. Over here I said r, and 0. When I factor out the r, the middle entry should be a 1. The middle entry should be a 1, sorry. So when I dot it with 1, 1, 0, get negative 1, 1, and 0. Negative 1 plus 1 is 0, plus another 0 is 0. Looking good. Now I take x1 and I dot it with x2. That product is 0, that product is 0, that product is 0. 0 times 1 is 0. Add up those three zeros, you get 0. The eigenvectors were 0. Now, this problem would have been a little bit more interesting if I had, say, the characteristic polynomial not being x times lambda minus 1 times lambda minus 2. It would have been more interesting if I had lambda cubed and lambda minus 1 squared and just lambda minus 2 to the first. That is, I didn't have eigenvector say that x0 came up 3 times? When I write down the eigenvectors from the distinct values, 0, 1, and 2, not 0, 0, 0, x minus 1 was squared, so 1, 1, and then 2. Not these 6 eigenvalues. Because if I find the eigenvector when x is 0, and then when x is 0, and then x is 0, I would have x of 0 3 times. Okay? And when you dot x0 with x0, another eigenvector, you won't get the 0 vector. You won't get 0. So there was an example where, since A was symmetric, it turned out that the eigenvalues that you didn't repeat were orthogonal. I'm going to write down a definition and take it from there. Okay, the definition says the following. A non-singular matrix A is called an orthogonal matrix. If A inverse is A transpose. That is, the inverse of A is A transpose. That is, A times A transpose equals identity. That is what is meant by an orthogonal matrix. A inverse must equal AT. Why do they say a non-singular matrix A? Because if you are singular, you can't have an inverse. And if you don't have an inverse, what are the chances that A inverse is going to equal A? A inverse can only possibly be A if A inverse can only possibly be A transpose if A inverse exists. Okay, so now let's note the following. I think this is important. A inverse equals A transpose. Well, if I multiply on the left side by A, if I multiply on the left by A, so I take A inverse and I multiplied by A on the left, and I took A transpose, and on the left I multiplied by A. But that means the identity is equal to A times A transpose. Now I could have gotten here a bit quicker, because when you multiply A by A inverse, you get identity. Okay? That must be A inverse. Because whatever you multiply A by to get the identity is called A inverse. But they're telling us we call A inverse is A transpose. See here, A times A transpose equals I. Whenever you have that, you have an orthogonal matrix. Because by the definition that's usually written up in a book, says that A inverse equals A transpose. That's the typical way to define an orthogonal matrix. A inverse equals A transpose. But that's the same as, if and only if, that's the same as A times A transpose equals I. So if you have a matrix and you notice that A times A transpose is I, you say, oh, this is an orthogonal matrix. I remember that guy talking about it. Okay. Now, here's an example. If A is equal to 2/3, negative 2/3, 1/3, 2/3, 1/3, negative 2/3, 1/3, 2/3, 2/3. If that's A transpose, interchange rows and columns. Instead of that row, I'm going to write it as the first row, I'm going to write as the first column. The second row, I'm going to write as the second column. The second row of A, I write down as the second column of A transpose. And the third row of A, I write down as the third column of A transpose. Well, if you actually bothered to multiply these out, A times A transpose is equal to I. Since the first matrix A is 3 by 3, and the second matrix A transpose is also 3 by 3, the inner numbers are the same, you're going to get the outer numbers. You're going to get a 3 by 3 matrix. Well, an identity matrix that is 3 by 3, we denote it by I. So A is an orthogonal matrix. I might be completely off on this next comment, but possibly they call it an identity matrix is because although you're not dotting these, you're multiplying them, and you're getting like 1. Oh, actually, you're supposed to get 0 when you dot. Okay, I'm not sure why they call it an orthogonal matrix. I was thinking of 1 because in an orthonormal set, the magnitude of each vector is 1. And identity is like 1. Okay. An orthogonal matrix is a matrix such that A times A transpose equals I, or alternatively, A transpose equals to A inverse. Now, let's talk about let's look at this example. Let's see what this example is going to show. Let us see what this example is going to show. Let A equal this matrix. 0, 0, negative 2, 0, negative 2, 0, and negative 2, 0, 3. Now notice, let's see what A transpose is. A transpose, well, I take the first row of A, which is 0, 0, negative 2, and write it as a column. I take the second row of A, 0, negative 2, 0, and write it as a column. And I take the third row of A, negative 2, 0, and write it down in the third column. And I look at these, and I say, oh, okay, they're equal. So A is symmetric. A is symmetric. Now, we can spend time finding the eigenvalues and the eigenvectors, but I'm just going to tell you what the eigenvectors are. The eigenvectors of A is this set. The set that contains 0, 1, 0, negative 1, 0, 2, and 2, 0, 1. This set is orthogonal. Okay? This set is orthogonal. Now, if we normalize these, normalizing yields. Now, normalizing means we just want to get those vectors to be unit vectors. Well, the length of 0, 1, 0, 0 squared plus 1 squared plus 0 squared square root underneath the radical is 1. The square root of 1 is 1. So, we can leave 0, 1, 0 alone. But let's look at negative 1, 0, 2. What is the length of that? If you're really quick on this, you can see that it's just going to be the square root of 5. Okay? What is the length of negative 1, 0, 2? Well, you square negative 1, you get 1. You square 0, you get 0. You square 2, you get 4. So it's 1 plus 0 plus 4 is 5 that's underneath the radical. So what I'm going to do is I'm going to take every entry, every component of negative 1, 0, 2, and I'm going to divide by the length. And remember, 0 divided by square root of 5 is just 0. Okay, now let's play the same game with the last vector. Let's find its length. And hopefully you realize it's going to be the same result. Remember, whether you square a positive number or a negative number, whether you square 3 or negative 3, negative 2/3 or positive 2/3, you're going to get the same answers. So ignoring signs, we have the same three numbers here, 2, 0, and 1. Fair enough, the order is different, but that doesn't affect adding. This is 5. Square root of 5. So I take 2, I divide it by square root of 5. That 2. I take 0 divided by square root of 5. I get square root of 5 still. And I take 1 and I divide it by square root of 5. Okay. This is an orthonormal set of vectors. Normal set of vectors. Okay, and that's obvious because if you take an orthogonal set of vectors, if this is an orthogonal set of vectors, and you normalize it, you make them unit vectors by just dividing by their lengths, the dot product will still be 0. Again, let me just make that clear. Let me try to prove that. First, let me put back what somehow got erased. If you come to know that x, y, z dotted with a, b, c, if you come to know that this is 0, that means x times a plus y times b plus z times c is 0. Well, if I multiplied by q times xa plus yb plus zc, that's going to equal to, I have to multiply the other side by q as well. The q times 0 is 0. But this is the same as qxa plus qyb plus qzc equals 0. In fact, let me invoke the associative law. That is, I can multiply this vector by q. And the dot, or divide by q. Multiplying by q is the same as dividing by 1 over q. If you preferred, I could have multiplied by 1 over q. So it's really 1 over q times x. It's 1 over q times x. It's 1 over q times y. I mean, it doesn't matter. If you want to see it in the denominator, you may have it in the denominator. 1 over qx, 1 over qy, 1 over qz. The dot product will still be 0. The dot product will still be 0. And that's all I did, is I divided some terms by the square root of 5, which means I multiplied by 1 over square root of 5. Dividing and multiplying, same operations. That is, if some fact is true about multiplication, it's also true about division. If some fact is true about division, it's gonna most probably be true. Well, let me not say that. I mean, multiplication commutes and division does not. What I'm saying is, anytime you multiply, you can also divide. Anytime you divide, you can multiply. Okay, so we have, and I want to write it down so we can read it. We have an orthonormal set of vectors. Okay. Now, if you take P inverse and you multiply it by A, and then you multiply it by P, what you are going to get once again is a diagonal matrix, and what's on the diagonal, those are going to be the eigenvectors. And I do want to say one thing. I guess I should say what P is. P is this matrix. P is this matrix of orthogonal vectors. orthonormal vectors. Of course, maybe I shouldn't have the brackets or commas. Okay. That matrix right there is the P. This is P. And it's just really nice how everything comes together. Okay, let's prove another theorem. Just let me state the next theorem. Theorem. We'll call these the theoretical exercise. Theorem. If A is an orthogonal matrix, then the determinant of A is plus or minus 1. Okay, now, to prove these things, you really have to know the definition. A is an orthogonal matrix implies that A inverse is equal to A transpose. Okay? Now, I is equal to A times A inverse. Oh, you know, I want to do it slightly different. Okay, first of all, recall one thing. Recall that the determinant of A and the determinant of A transpose are the same. Okay. So now, the determinant of A squared is equal to the determinant of A times the determinant of A. But the determinant of A is the determinant of A transpose. I'm going to keep the first determinant of A the same. And instead of that A, I'm going to write A transpose. But here's where it comes together. Now this is always true, orthogonal matrix or not. The determinant of A can always be replaced with the determinant of A transpose. But in this case, determinant A transpose and A inverse are the same. So the determinant of A transpose is the determinant of A inverse. But the determinant of one matrix times the determinant of another matrix is the determinant of their product. I mean, after all, okay, now A times A inverse is I, and the determinant of I is 1. So the determinant of A transpose is 1. There's only a couple of numbers out, when you square them, give you 1. Okay, so the determinant of A transpose equals 1. But that implies the determinant of A is either 1 or negative 1. And that is what I wanted to prove. The determinant of A is plus minus 1. Now we want to show that if A and B are orthogonal matrices, then their product is orthogonal. because they have to be of the right size. Okay, they have to be of appropriate sizes. Okay. Theorem. Well, maybe not, because I'm saying show. Show that if A and B are orthogonal matrices, then AB is an orthogonal matrix. Okay. So remember, proof. A orthogonal implies A equals A transpose equal A inverse, and B orthogonal matrix implies that B transpose is B inverse. Now, what I want to show is that it happens with the product. If you multiply A and B together, the transpose is equal to the inverse. That is what I want to show. Okay. Now, AB transpose, we know, is B transpose times A transpose. But B transpose is B inverse. So instead of B transpose, I'll put B inverse times A transpose. But A transpose is A inverse. Okay, but we can switch the B into A or the A into B and say it's AB inverse. Remember, AB inverse, you switch the order, put B and then A, and then inverse each of these. So this, which clearly equals that, equals this. That's what I said it equals. Remember, you have to understand equality better than you know your name. If AB inverse equals that, then that equals AB inverse. That equals AB inverse. And that's what I wanted to show. I showed exactly what's on the bottom. If you take the transpose of AB, it's the same as taking the inverse of AB. Therefore, AB is an orthogonal matrix. That completes that proof. Okay, have fun with these. But before you can have fun, you have to know the definitions. If you don't know the definitions and the theorems and the properties, this is painful. The only reason I can easily do it, or somewhat easily do it, is I remember the properties. Remember that AB transpose is B transpose A transpose. AB inverse is B inverse A inverse. Know your properties and think a little bit, and you won't have any trouble. But you have to know your definitions and your properties and your theorems. And there's hundreds of them. So that's what makes it more fun. Okay, good luck.